Okay, so first I will start by defining what the law of conservation of energy actually is. The conservation of energy law tells us that the total energy in an isolated system is conserved. You've probably heard, even if you're not a physics student, the expression energy cannot be created or destroyed. That is exactly what that statement is referring to, is the law of conservation of energy. So what that means is that energy within a scenario that we are given, that we are evaluating, the starting amount of energy has to be equivalent to the final amount of energy. We don't gain energy along the way so long as we are dealing with an isolated system, which I will explain in a second, elaborate a little bit more on that term, but for the situations in which you're given in the grade 11 and grade 12 problems will be isolated. So when we talk about isolated system, it can literally mean a system or a scenario that is isolated, enclosed physically by 4 walls or however many walls, but enclosed by physical barriers, or a scenario or situation that is so far removed from any other external, influenced and altered by external forces. So when you're given conservation of energy questions, the scenario that they will give you in the question itself will be an isolated system. I'm going to give an example here, and I will use this example, the same example, to draw reference to throughout my entire explanation so you can see the nuances of what I'm explaining, the contrast within this one reference scenario. It's a stationary car, so a car not in motion at the top of the hill that rolls down the hill. So in this situation, for an isolated system, just to identify what the system is, it's that car and the hill. So the car at the top of the hill rolling to the bottom of the hill, that occurrence of what's happening in the two objects in play in that scenario, so the hill and the car, the two things of relevance, that is our isolated system. Okay, so now that we have the law out of the way and what we mean by the term isolated system, I'll go back to the definition one more time to draw another reference. So energy in this isolated system can't be created or destroyed. However, it can be transferred from one form to another form. And that's the entire basis for what these conservation of energy questions will be testing you on, will be based around, is that concept right there, that the energy doesn't get destroyed, but rather it gets transferred through one form or another. Back to our stationary car at the top of the hill rolling down the hill, coming to us at the bottom of the hill example, there are two types of energy at play in this situation. There's a lot more forms of energy in existence than just kinetic and potential. We have chemical, we have heat, not restricted to just kinetic and potential energy, but when you're first learning conservation of energy problems, those will be the two main ones that you will be using to solve for these questions. So I'll now get into the difference between kinetic and potential energy. So kinetic energy, you can think of kinetic motion, is the energy possessed by an object that has motion. For example, this car, if it's at rest and just is parked on the side of the road, it has no kinetic energy at the moment because it's at rest. However, once it's in motion, then it has a kinetic energy. So in order for kinetic energy to be present in the situation, we need motion of an object. Now, potential energy can have motion but isn't required to have motion like kinetic energy is. So we can't have kinetic energy if our object's at rest. We can have potential energy if our object's at rest, but it's not necessary that it be at rest in order for it to have potential energy. So potential energy versus our kinetic energy is the energy that's possessed by an object that has a vertical displacement. So the equations for kinetic and potential energy before, you'll notice in potential energy's equation there's a letter H. So that H stands for height, and they mean the vertical height, the vertical displacement of an object from a reference point. So from a horizontal, from whatever your base horizontal line is in your situation, whether that be the ground or the x-axis on a grid system, there needs to be movement up the y-axis, so vertically up. So I wanted to just make it clear that it needs to be a height difference vertically and not horizontally, because obviously that's not a height difference, but sometimes sometimes students will get confused and think that there's potential energy if a car is moving and it's moving horizontally. No, that scenario would be entirely kinetic energy, no potential energy. So maybe you're already starting to intuitively see here how kinetic and potential energy are at play in this scenario with the car. This is going to be the diagram of that car, starting at the top of the hill, and then he rolls down and finishes at the bottom of the hill. So we start with energy potential up here, which is proportional to the mass of the car times gravity, which is 9.8 meters per second squared, and then the height of the car, how far it started up from the horizontal. So this distance here, so that height, whatever that is, we're going to say it's 20 meters. H value, that's going to go up into our potential energy equation to figure out the energy of the car at the top of the hill when it's at rest. Then it's going to roll down to the bottom of the hill, and by the time it reaches the bottom, its energy will be completely converted into kinetic energy, so energy of motion, and that equation is 1/2 mass. So the same m that you used up here for the mass of the car is going to be the m you used down here, and then velocity squared, and that will be the velocity of the car. So we're going to let, in this instance, the mass of the car be 1,500 kilograms. Units should be in kilograms because we're going to find our energy, our units for energy in joules. So our unit for mass will be in kilograms. Our gravity is 9.8 meters per second squared, and then our height, which was, as I mentioned earlier, 20 meters. We're going to let it be in this case. So that's our scenario. We can see what it looks like. So with that, we will say our total energy to start, which happens to be potential in this situation coming from the top of our hill. We will calculate what that is. So we have a magnitude to solve for our after the event information. So I have the one variable we don't have information for given in this scenario, in this question, is our velocity. We don't know what that is. So that one last variable being unknown, that's going to be what we have to solve for. So in order to do that, we will find out what the magnitude of energy is up here, and then once we have that value for E in joules, we will plug it down into this equation, this E for this equation, and then we can isolate for velocity, and that will complete the missing piece of information in our scenario. So anyways, back down to what we're doing here. So our starting energy is potential, so that equation is mgh. So all I'm going to do is sub those three numbers in, make sure my units match up, which we already did, but I plug that into my calculator. I get a number of 294,000, and I'm going to leave that in joules. You can change that. You could convert that to kilojoules at this point. It's a large enough number, but we will leave unit conversion for another video. So that was our starting energy, and now we're going to find our final energy. So starting energy happened up here, part 1. Now we're going to find part 2 energy. So now we're going to employ our kinetic energy equation. So E final, which is going to be kinetic, is equal to 1/2 m mass, v squared, velocity squared, and we're going to take that energy that we solved for at the start with all our given information, that energy, and plug that in to this value for energy. So I have 294,000 in for my E final position. 1/2 is just 1/2. Mass is going to stay the same as what we originally had for the car, so 1,500 kilograms, and velocity is what we're going to be solving for. So I want to isolate velocity. So when I do that, I end up getting 392. Now, this number here is equivalent to velocity squared. So we account for that by getting rid of the squared here and square rooting that number. So if you want an exact answer, you can leave it as this radical, but if you want a decimal answer, what you end up getting is approximately 19.8 meters per second, and that's the velocity. So that's the highest velocity once all of my potential energy from when it was at rest gets converted to kinetic energy, that's the velocity this car is going to be moving at, 19.8 meters per second.